Mars has been visible in the evening sky for most of human history, a faint reddish point of light that people have stared at and wondered about for thousands of years. Ancient civilizations named it after gods of war. Astronomers mapped its surface from Earth, and for the last several decades we have been sending robots there, one after another, learning everything we can about a world that sits just close enough to feel almost reachable. Pathfinder, spirit, opportunity, curiosity, perseverance, each mission more capable than the last, each one returning data, images, evidence that Mars was once warmer, wetter, and more hospitable than the frozen desert it is today. And now, for the first time in history, the technology to actually send humans there seems genuinely close. SpaceX is building a rocket large enough to carry a crew. NASA has a roadmap. Engineers are talking about the 2030s not as science fiction, but as a real operational window. The dream of humans standing on Martian soil, looking up at a sky that is the wrong color, breathing recycled air inside a suit, knowing they are the first. That dream has never felt more plausible. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. But there is something that almost nobody talks about in the press conferences and the glossy mission animations. Every documentary about Mars colonization lingers on the launch, on the landing, on the first boot print in red dust. The cameras pull back dramatically, the music swells, and then the video ends. What almost nobody shows you is what comes next, not the exploration, not the science. What comes after that? Getting home. Here is what most people don't realize. The journey to Mars, as staggering as it is, may actually be the simpler half of the equation. The real engineering nightmare, the part that has quietly kept mission planners awake for decades, is the return. Getting a small group of human beings off the surface of another planet, through Martian orbit, across hundreds of millions of miles of deep space, safely back to Earth requires a sequence of operations so complex, so expensive, and so dependent on technology that has never been demonstrated anywhere, that some of the most serious engineers and space policy researchers in the world have begun to ask a question out loud that nobody wants to hear. Is a return mission actually feasible? Not in theory, not on paper, in practice, with real hardware, on a real timeline, with a real budget that a real government or company would actually sustain for 2 decades without canceling it? The honest answer is that nobody knows. And that uncertainty is not a minor footnote. It sits at the center of every human Mars mission architecture ever proposed. The return journey is responsible for the majority of the mission's mass requirements, most of its cost, nearly all of its most dangerous unproven technologies. Strip out the return component, and a Mars mission becomes dramatically simpler, dramatically cheaper, and dramatically more achievable. Add it back in, and the complexity multiplies in ways that are genuinely hard to overstate. That is the tension running through everything that follows. Not whether we can reach Mars. That problem is largely solved. The question is whether we can bring the crew back. And if the answer turns out to be no, or not yet, or not without conditions that no government will fund and no engineer can guarantee, then the first humans to land on Mars may arrive there knowing they are not coming home. Getting to Mars might actually turn out to be the easy part. Mars is not simply far away in the way that people casually say things are far away. When people say Antarctica is far away, they mean it takes a long flight. When they say the moon is far away, they mean 3 days in a spacecraft. Mars is something different. Mars is far away in the way that changes the entire nature of what a mission means, what risk means, what commitment means. The distance isn't just a number on a chart. It's a constraint that reaches into every single aspect of a crewed Mars mission. and it starts before the crew even leaves the ground. Let's start with something concrete. The International Space Station orbits about 250 miles above Earth's surface. If something goes wrong up there, a crew can be home in a few hours. They board a Soyuz capsule, undock, and they're back on the ground before the day is out. The moon is roughly 239,000 miles away. The Apollo astronauts took about 3 days to get there. When Apollo 13 lost its service module, the crew was still able to loop around the moon and coast home. 3 days. That's how long it took before they were back in Earth's atmosphere. Now consider that Mars, at its closest approach to Earth, sits about 35 million miles away. At its farthest, it's over 250 million miles. There is no emergency undocking. There is no 3-day return. There is no coming home early. The lowest energy path from Earth to Mars follows what's called a Hohmann transfer orbit. You don't fly in a straight line. You launch into an elliptical arc that carries your spacecraft from Earth's orbit out to Mars's orbit, coasting most of the way on the momentum of your initial burn. It's efficient. It's also slow. That transfer takes roughly 9 months. 9 months of continuous travel through deep space inside a spacecraft before you see a planet beneath you again. That's not 9 months with regular supply runs or crew rotations. That's 9 months completely committed, completely underway, completely committed to arriving somewhere you've never been before. And here's what makes the return trip genuinely different from any mission humans have ever flown. You can't just turn around. The planets don't wait. Earth and Mars orbit the Sun at different speeds, and they only line up for an efficient return journey roughly once every 26 months. That window lasts a limited time. Miss it, and the next one is more than 2 years away. So when a crew lands on Mars, they aren't waiting a few weeks or even a few months for the next ride home. They are waiting approximately 500 days on the Martian surface before the geometry of the solar system allows a fuel-efficient return at all. 500 days. That's not a detail that gets mentioned in press conference highlights. It's the core of what makes a Mars mission unlike anything else in the history of human spaceflight. Add it all up, 9 months to get there, roughly 500 days on the surface, 9 months to return. The total comes to somewhere around 34 months. Nearly 3 years, start to finish, if everything goes right. Think about what 3 years means in practical terms. 3 years of food, water, oxygen, medical supplies, spare parts, psychological stability, and working hardware. All of it brought from Earth or produced on Mars. All of it completely cut off from resupply the moment the spacecraft leaves Earth's orbit. There are no convenience stops. There is no resupply ship coming in 6 weeks. Whatever the crew has when they leave is what they have for the entire mission. Compare that to anything in the history of human spaceflight, and the scale becomes hard to absorb. The longest continuous stay aboard the International Space Station is around a year, and those astronauts were 250 miles from home, resupplied regularly, and could be evacuated in an emergency. A Mars crew would be none of those things. Scott Kelly spent nearly a year in space and came home with measurable changes to his body, his vision, and his physiology. The first Mars crew would spend more than 3 times as long away from Earth, in an environment far more hostile than low Earth orbit. The Apollo astronauts were brave beyond most people's comprehension, but they were also never more than 3 days from home. That changes the psychology of a mission in ways that are hard to fully articulate. You are never truly stranded when you are 3 days from home. You are never truly alone. You always have a return. The first humans to set foot on Mars will have no such anchor. The moment their spacecraft leaves Earth, they are committed. The window closes. The trajectory locks in. There is no coming back early because something feels wrong, because someone gets sick, because a piece of equipment is behaving strangely. You are going to Mars, you are staying on Mars for 500 days, and then you are coming home on the schedule the solar system permits, not the schedule you might prefer. That locked-in quality is what separates Mars from every human spaceflight mission that has come before it. It's not just about the distance in miles. It's about the distance in time and in options and in the fundamental question of what you do if something goes wrong after the window has closed. Once you leave Earth for Mars, you cannot come home whenever you want. And that single constraint creates nearly every other problem on this list. The first question any serious Mars mission designer has to answer is how much mass you actually need to move. The answer is almost incomprehensibly large. Think about what a crewed Mars mission actually requires. You need a spacecraft large enough to keep people alive for 9 months of deep space transit. You need food, water, oxygen, medical supplies, and radiation shielding. You need fuel for course corrections along the way. You need landing hardware, surface habitat equipment, power systems, and scientific instruments. And you need enough margin in every single category to survive the unexpected. This was because on a mission to Mars, the unexpected will happen. When engineers start adding up the numbers, they arrive at a mass requirement that dwarfs anything humanity has ever attempted to send beyond Earth orbit. The Apollo spacecraft that carried astronauts to the moon weighed roughly 45 metric tons at launch. A crewed Mars mission, depending on the architecture, requires somewhere between 500 and 1,000 metric tons of total mass just to get the mission off the ground. SpaceX's Starship is currently the only vehicle being developed that could plausibly carry a human crew to Mars. It's a remarkable machine. Fully loaded, it can carry up to 100 metric tons of payload. That's more than any rocket ever built. And it still isn't enough, not even close. A single Starship, even fully fueled, does not carry enough propellant to complete the journey from Earth orbit to Mars on its own. The vehicle needs to be topped off in orbit before it departs. And topping off a Mars-bound Starship doesn't mean one refueling flight. It means 12 separate tanker launches. Each tanker is itself a full Starship mission, launching from the ground, reaching orbit, transferring 100 metric tons of cryogenic propellant to the waiting spacecraft. That's 1,200 metric tons of propellant delivered in orbit before the Mars mission can even begin its journey. Each of those 12 flights has to succeed. The propellant transfer has to work correctly every single time. The orbital rendezvous procedures have to execute without failure, and all of it has to happen within a specific launch window because the planets don't wait. Cryogenic propellants don't sit patiently in a tank. Liquid oxygen and liquid methane are extremely cold, and they slowly boil off over time. That means the 12 tanker flights cannot be spread out over months. They have to happen in rapid succession, each one arriving and transferring its load before too much of the previous delivery has been lost. Coordinating 12 orbital launches in a compressed time frame with 0 critical failures is an operational challenge that has no precedent in the history of spaceflight. The International Space Station. That is the most complex construction project ever completed in orbit. Took more than a decade and dozens of missions to assemble. What's being described here is something of comparable complexity compressed into weeks. Here's what most people don't realize. Humanity has never transferred cryogenic propellant between 2 vehicles in orbit. Not once. It's a technology that exists on paper, has been studied extensively, has been tested in limited ways on the ground, but it has never been demonstrated at scale in the actual environment where it needs to work. SpaceX has been developing the techniques. The tests are ongoing, but 12 successful orbital propellant transfers, one after another. With a human mission waiting in orbit, is a different order of problem than any test ever conducted. And the launch cadence itself creates compounding risk. Each of those 12 tanker flights is a rocket launch. Rocket launches fail. The history of spaceflight, even for the most reliable vehicles ever built, includes failures. Statistically, across 12 flights in close succession, the probability of at least one anomaly is not zero. If one tanker launch fails, the mission loses 100 metric tons of propellant. If it fails early in the sequence, the window may still allow a replacement flight. If it fails late in the sequence, the Mars-bound spacecraft may have to depart underfueled or scrub the window entirely and wait another 26 months. The human crew, if they're already in orbit waiting, would have to return to Earth and the entire sequence would have to restart. None of this is a reason the mission can't be done. It is a reason the mission is genuinely deeply difficult in ways the promotional presentations tend to compress into a few slides. When Elon Musk describes sending humans to Mars, the 12-tanker refueling architecture is real. The plan is serious. But the gap between having a plan and executing it without a single mission-ending failure across that many interdependent operations is the gap between a concept and a capability. What this all means is that even the departure, just leaving Earth for Mars, represents a logistical undertaking that would rank among the most complex operations in the history of human spaceflight, before anyone has endured 9 months of deep space radiation, before anyone has attempted to land 50 to 100 metric tons on a planet with an atmosphere too thin for parachutes and too thick to ignore, before anyone has tried to manufacture rocket fuel on another world. Before any of that, the mission has already required 12 successful orbital launches, 12 successful propellant transfers, a coordinated sequence of operations with no historical equivalent, and that is before a single human being has set foot on Martian soil. Assuming the spacecraft and crew survive the 9 months of deep space travel, they still have to land. That sentence sounds simple. It is not simple. Landing on Mars is one of the most technically brutal problems in all of spaceflight, and the reason comes down to a single frustrating fact about Mars's atmosphere. It's too thin to stop you and too thick to ignore. On Earth, if you're falling from orbit, the atmosphere does most of the work. It's dense enough that aerodynamic drag bleeds off your velocity over time. A heat shield and parachutes can handle the rest. On the Moon, there is no atmosphere at all, which is actually easier in some ways. You know exactly what you're dealing with, and you just fire your engines until you stop. Mars sits in the worst possible middle ground. Its atmosphere is about 1% as dense as Earth's. That sounds like almost nothing, and for deceleration purposes it largely is, but it's still enough to generate enormous heat on the way in. You need a heat shield. You need aerodynamic deceleration. You also need parachutes, because every bit of drag helps. And then, because the atmosphere runs out of usefulness while you're still moving far too fast, you need rocket engines as well. You need all of these things in sequence working in perfect coordination over a span of roughly 7 minutes. NASA engineers have a name for those 7 minutes. They call it the 7 minutes of terror. You enter the atmosphere at around 13,000 miles per hour. You have 7 minutes to reach zero. Every phase of the sequence has to trigger at exactly the right moment. The heat shield, the parachutes, the separation of the back shell, the ignition of the descent engines, the radar altimeter readings feeding into the guidance computer, the final touchdown. Each step depends on the previous one. There is no pause button, there is no rewind, and there is no help from Earth, because even at Mars's closest approach, a radio signal takes at least 3 minutes one way. By the time Mission Control receives your first transmission from the top of the Martian atmosphere, you have already been on the surface for several minutes, either safely down or destroyed. The computer has to do it alone. Every decision, every trigger, Every course correction happens autonomously, faster than any human can respond. Engineers on the ground can only watch the data come in after the fact and find out what happened. Multiple spacecraft have not survived this sequence. Mars has a long list of missions that were functioning perfectly in cruise and simply vanished during those 7 minutes. The Soviet Mars 2 and Mars 3 landers. Beagle 2, which actually made it to the surface but failed to deploy properly. Schiaparelli, which crashed in 2016 after a software error, caused the descent engines to shut off too early. These were small robotic missions. They weighed hundreds of kilograms. They had no crew, and they still failed. Every Mars lander or rover that has successfully reached the surface has weighed less than roughly 1 metric ton. Curiosity weighed about 900 kilograms. Perseverance, the largest and most capable rover ever sent to Mars, came in at approximately 1 metric ton. That is the current state of human capability for landing things on Mars. 1 metric ton. That number matters enormously. A crewed Mars mission requires landing somewhere between 50 and 100 metric tons on the surface. That is not a modest improvement over what we've done before. It is a leap of 50 to 100 times beyond the heaviest payload ever successfully landed on another planet. The heat shield alone for a vehicle that size would need to be larger than anything ever flown. The parachute system would need to handle forces that no parachute has ever been designed to handle in a Martian entry environment. The descent engines would need to throttle and vector with extraordinary precision while managing a mass that dwarfs anything previously attempted. And here is what makes this particularly difficult to solve. You cannot test it on Earth. You can test pieces of it. You can fire engines in a vacuum chamber. You can model heat shield performance computationally. You can run parachute tests in high-altitude balloons. But you cannot replicate the actual Mars entry environment on Earth because Earth's atmosphere is fundamentally different. The pressure profile is different. The density is different. The chemical composition is different. The way shock waves form around a heat shield at Martian atmospheric densities is not something you can reproduce in a wind tunnel. NASA engineers describe the constraint plainly. You cannot test as you fly. The full system, heat shield, parachutes, descent engines, guidance computers, landing legs, can only truly be validated on Mars. The first time the system operates in the actual Mars environment will be the first time it has ever operated in the Mars environment. It has to work. Think about what that means for a crewed mission. The astronauts inside that vehicle will have spent 9 months getting there. They will have endured radiation exposure, bone density loss, the psychological weight of being millions of miles from Earth. And then they will strap in for 7 minutes and hand complete control to a computer in an atmosphere that has destroyed spacecraft before, using a landing system that has never been operated at this scale, in this environment, under any conditions. The engineering challenge of scaling from 1 metric ton to 50 is not just a challenge of making things bigger. Every subsystem has to be rethought. The aeroshell that protects the vehicle during atmospheric entry has to be larger than any aeroshell ever flown. The guidance system has to perform more precisely because the vehicle is heavier and less forgiving of errors. The engines have to be more powerful and more reliable. The whole choreography has to be redesigned from the beginning. Every successful Mars landing in history has involved a payload of roughly 1 metric ton or less. There is a hazard in deep space that you cannot fully engineer your way around, and it has been quietly worrying mission planners for decades. It doesn't look like anything. You can't see it. You can't feel it. There's no warning system that tells you when it's arriving. It passes through the walls of a spacecraft the way light passes through a window. It passes through the human body the same way. And it is accumulating the entire time, every hour of every day of the journey, in both directions. It's called galactic cosmic radiation. These are high-energy particles, protons, helium nuclei, and heavier atomic fragments, streaming in from outside our solar system, accelerated to extraordinary velocities by distant supernovas and other violent cosmic events. On Earth, you don't have to think about them. Earth's magnetic field deflects most of them long before they reach the surface. The atmosphere absorbs most of what gets through. You are living inside a radiation shield that is thousands of kilometers deep, and you've never had to consider it because it has always been there. The moment you leave Earth orbit, it's gone. In low Earth orbit, the ISS still sits inside the protective bubble of Earth's magnetic field. Astronauts there receive more radiation than people on the ground, but the shielding effect is still substantial. On the journey to Mars, there is no bubble. There is no magnetic field. There is just open space and the full intensity of the galactic cosmic ray environment hitting the spacecraft from every direction. The spacecraft walls provide some shielding, but here's what most people don't realize. Dense shielding material actually makes certain types of cosmic radiation worse. When high-energy particles hit metal walls, they produce secondary radiation, a cascade of new particles generated by the collision. The only shielding that helps without this secondary effect is mass. Water, polyethylene, material with lots of hydrogen atoms. And water is heavy. Adding enough water shielding to meaningfully reduce galactic cosmic ray exposure would add mass to the spacecraft on a scale that creates entirely new engineering problems. There is no clean solution. The radiation environment in deep space is, right now, something we cannot adequately shield against at any mass that a launch vehicle could reasonably carry. So how bad is it? NASA put a radiation detector called RAD, the Radiation Assessment Detector, aboard the Curiosity rover. It measured radiation not just on the Martian surface, but during the cruise phase, the deep space transit between Earth and Mars. The numbers it returned are sobering. A round trip to Mars, including time on the surface, would expose an astronaut to a minimum of 0.66 sieverts. That's the minimum. That's the floor. Under favorable conditions, with solar activity behaving cooperatively, with no major solar particle events, with everything going as well as it possibly could. NASA's recommended career radiation limit for astronauts is 0.6 sieverts. The minimum dose for a single Mars mission already exceeds the limit that NASA considers acceptable for an astronaut's entire working career. And that's the floor. The ceiling is considerably higher. A major solar particle event, a burst of intense radiation from the sun, can dramatically spike the dose received during transit. The galactic cosmic ray environment fluctuates with the solar cycle. Some mission windows are worse than others. The 0.66 sievert figure is not an average, it's a best case. NASA has modeled the health risks using those numbers. The results are not reassuring. Central estimates for radiation-induced mortality, meaning radiation that causes death, exceed 5% for a Mars mission. The upper confidence interval approaches 10%. That means there's a realistic scenario in which roughly 1 in 10 Mars astronauts dies from radiation-related causes, not during the mission. Later, cancer, cardiovascular disease, the body tallying the damage long after the astronaut has returned to Earth. The morbidity estimates are higher still. Morbidity means serious health effects that alter your life without necessarily ending it. The list is long. Cancer is the most familiar. But the radiation effects on a Mars mission also include cardiovascular disease, accelerated by damage to blood vessel walls, cognitive decline, high-energy particles punching through brain tissue, severing neural connections, disrupting function in ways that don't show up immediately but accumulate over years. Vision problems, cataracts, fertility issues, disrupted sleep architecture, compromised immune response. These are not theoretical concerns. They've been observed in astronauts returning from far shorter missions. On the Martian surface, there's some relief. Mars has a thin atmosphere, about 1% of Earth's atmospheric density, and it does absorb a fraction of the incoming radiation. The surface offers some protection that open space does not. During a dust storm, when the atmosphere thickens with suspended particles, astronauts staying indoors receive a somewhat reduced dose. But the dust storm protection is partial at best, and the surface phase of the mission is only a portion of the total exposure. The transit phases, 9 months out, 9 months back, are the worst. Those 18 months in deep space with no planetary body nearby and no magnetic field overhead are when the radiation accumulates fastest. Here's what makes this particularly difficult. It's invisible. There's no physical sensation. An astronaut receiving a harmful dose of galactic cosmic radiation feels nothing different in that moment than an astronaut receiving a safe dose. The damage is happening at the cellular level, in DNA, in blood vessel walls, in neural tissue. The body doesn't register it as pain. You won't know the cost until years later, when the biological accounting finally comes due. Mission architects have explored every option. Water walls, polyethylene panels, storm shelters, small, heavily shielded compartments where the crew retreats during solar particle events. These help with some threats. They don't solve the galactic cosmic ray problem. They reduce it at the margins. The fundamental physics hasn't changed. Galactic cosmic rays are highly penetrating, abundant, and inescapable in the deep space environment that a Mars mission requires. A single Mars mission would expose astronauts to more radiation than NASA considers acceptable over an entire career. Radiation is not the only thing working against the human body on a mission to Mars. The radiation threat is real and well documented. But even in a perfectly shielded spacecraft, the human body would still be falling apart in other ways. Space does not need radiation to damage you. It can do plenty of damage on its own. Start with bone. On the International Space Station, astronauts lose somewhere between 1% and 2% of their bone mineral density every single month. Every month. And that is with a structured exercise regimen that takes up hours of every single day. Resistance machines, treadmills, cycling equipment, all of it bolted into a space station specifically to slow the losses down. With all of that, the bones still thin. A 9-month transit to Mars would cost an astronaut somewhere between 9 and 18% of their bone density before they even arrive. They land on Mars already compromised, already structurally weaker than when they left Earth. The skeleton they relied on their entire lives has been quietly hollowing out for months. And then there is muscle. The human body is extraordinarily efficient at discarding what it doesn't need. In microgravity, the muscular system is not being loaded the way it was designed to be loaded. Muscles that spent decades fighting gravity suddenly have almost nothing to fight. They atrophy, they shrink. The legs are particularly vulnerable because on Earth, the legs carry the entire weight of the body with every single step. In weightlessness, they carry nothing. The losses are relentless, and they begin almost immediately. But here's what most people don't realize about the physiology. It's not just the skeleton and the muscles. Fluid shifts in the body when gravity disappears. On Earth, gravity pulls blood and fluid toward the lower body. Remove gravity, and that fluid migrates upward, toward the head and chest. Astronauts describe it as a constant feeling of head congestion, like a permanent mild cold. But the effects go deeper than discomfort. The fluid redistribution increases pressure inside the skull. That intracranial pressure bears on the optic nerve, on the eye itself, on the structures behind it. Astronauts have returned from long-duration missions with permanently altered vision. The eyeball changes shape, the optic nerve swells. NASA calls this spaceflight-associated neuroocular syndrome. Some astronauts come home needing glasses they didn't need before they left. Some never fully recover their prior vision. For a Mars mission, you are talking about 9 months of this pressure building on the transit out, another stretch during the return journey. The damage accumulates over time. Now consider the paradox waiting on the surface. Mars has gravity. Not much, about 38% of what Earth has, but it exists. That sounds like a partial reprieve, and in some ways, it is. The fluid shifts improve. The body is no longer in true microgravity, but 38% of Earth's gravity is still not enough to maintain Earth-normal bone density and muscle mass. The losses slow down on Mars, but they do not stop. The body adapts to the Martian environment over weeks and months. It recalibrates. What is normal begins to shift. An astronaut who spends 16 months on the Martian surface is not just a person who has been away from Earth for a while. They are a person whose entire physiological baseline has been quietly, steadily resetting toward a different gravitational environment. Think about what that means for the return. Assume everything works. Assume the ISRU equipment produced the propellant. Assume the ascent vehicle fires and reaches orbit. The crew boards the return vehicle and begins 9 more months of microgravity transit back toward Earth. Whatever conditioning they maintained on Mars is now being undone again. The bones thin again. The muscles atrophy again. The fluid shifts again. By the time they enter Earth's atmosphere, they have spent roughly 9 months in microgravity outbound, 16 months in partial gravity on the surface, and 9 more months in microgravity on the return, 34 months total. That is nearly 3 years of reduced or zero gravity loading on a body that evolved under a full 1G of force. The moment they land, Earth does not care where they have been. Earth's gravity does not ease them in. It pulls on them at the full 1G it has always pulled at, and the bodies receiving that force are not the bodies that left. Bones that have lost 15 or 20% of their density are now being asked to support full Earth weight again. Muscles that have not been fully loaded in years are being asked to hold a person upright and move them through a full gravitational field. The cardiovascular system, which adapted to pumping blood in a low-gravity environment, suddenly has to work against a far heavier column of fluid. Returning astronauts from long ISS missions often cannot walk off the spacecraft. They are carried. They spend weeks in rehabilitation just to function normally on the planet where they were born. A Mars mission is not 6-months HS on the ISS. It is nearly 3 times longer at varying but consistently reduced gravity levels. By the time the first Mars astronauts finally return to Earth, their bodies may have partially forgotten what it felt like to live here. There is one problem with a Mars mission that no amount of engineering or money can solve. It has nothing to do with propellant or landing systems or radiation shielding. It is a consequence of physics itself. The speed of light is the fastest anything in the universe can travel. Radio signals move at the speed of light, and the distance between Earth and Mars means that even at that speed, communication takes minutes, sometimes many minutes. When Mars is at its closest approach to Earth, a one-way signal takes about 3 minutes to arrive. 3 minutes sounds manageable, but when Mars swings to the far side of its orbit, that delay stretches to 24 minutes one way. Ask a question. Wait 24 minutes for the signal to reach Earth. Wait another 24 minutes for the answer to come back. That is a 48-minute gap for a single exchange. There is no technology that fixes this. There is no faster antenna, no better receiver, no engineering solution under development. The delay is the distance, and the distance is not going anywhere. Think about what this meant during Apollo 13. A service module exploded 200,000 miles from Earth. The crew had a limited window to survive. Mission Control in Houston stayed on the line continuously, working the problem in near real time. Engineers calculated abort trajectories, flight directors made decisions. The astronauts and the ground were solving the same problem together, almost simultaneously. That constant back-and-forth communication is part of why the crew came home. The moon is close enough for conversations. Mars is not. When the first Mars crew encounters a serious malfunction, and on a 34-month mission something serious will fail, they will not be able to call Houston and talk it through. By the time the signal from the crew reaches Earth, 10 or 20 minutes have already passed. By the time Houston transmits a response, another 10 or 20 minutes pass. The crew has been dealing with the emergency for half an hour or more before they hear a single word of guidance. In a fast-moving systems failure, half an hour is the difference between a manageable situation and a catastrophe. This changes the entire philosophy of how a Mars mission has to be designed. The crew cannot rely on ground support the way every previous crewed mission has. They have to be capable of diagnosing and solving any emergency on their own, using only the equipment and knowledge they brought with them. That means more extensive training than any astronaut has ever undergone. It means more redundant systems, more backup hardware, more spare parts. All of that means more mass. More mass means more fuel. More fuel means more launches, more cost, more complexity. The communication delay does not just create a psychological problem. It cascades through the entire mission architecture. There is a psychological dimension to this that is genuinely hard to overstate. Every astronaut on the International Space Station can call home. They can speak to their families, receive support, hear a familiar voice. They are 250 miles above Earth, close enough that a conversation feels like a conversation. A Mars crew would be tens of millions of miles away from anyone. Communication would feel less like talking and more like sending letters and waiting. And in an emergency, that isolation would be total. No reassurance from the ground, no real-time guidance, no voice in the earpiece walking them through the steps. Analog studies have tried to simulate this. Researchers living in Mars-like habitats with enforced communication delays report that the experience fundamentally changes how the crew operates. Decisions that would normally involve ground support have to be made independently. Problems that would normally be escalated have to be solved in the habitat. The crew becomes its own isolated world. That is not a technical failure. That is the actual operating environment of a Mars mission every day for nearly 3 years. When something goes wrong on Mars, and something will go wrong, the crew will face it entirely alone. To understand why returning from Mars is so difficult, you have to understand the math of rocket propellant. Not the general idea of it, the actual numbers. Because when you see the numbers, something shifts. The problem stops being abstract and starts being almost physically uncomfortable to think about. A return mission from the Martian surface requires at least 1,200 metric tons of propellant. That is the minimum estimate. Not a worst-case figure, not a pessimistic projection. The floor. And here is what makes that number so staggering. You cannot bring 1,200 metric tons of propellant from Earth. The math does not allow it. Every kilogram of mass you launch from Earth costs an enormous amount of fuel just to escape Earth's gravity. Then it costs more fuel to reach Mars. The deeper you push into a gravity well, the more expensive every kilogram becomes. Engineers have calculated that launching approximately 400 metric tons of propellant from Earth would deliver roughly 35 metric tons of usable propellant to the Martian surface. 35 metric tons out of 400. That is the exchange rate that Earth's gravity imposes on you. And 35 metric tons is nowhere near the 1,200 that the return journey requires. Think about that for a moment. 400 metric tons of fuel lifted from Earth to deliver 35 metric tons to Mars. That ratio alone tells you that an Earth-provisioned return mission is not just expensive, it is effectively impossible at the scale required. You cannot launch enough rockets, burn enough fuel, or spend enough money to bridge that gap from the Earth side of the equation. There is only one practical answer. You have to make the propellant on Mars. This is what engineers call in situ resource utilization, or ISRU. The concept is straightforward. Mars has resources. Carbon dioxide makes up about 95% of the Martian atmosphere. Water ice exists below the surface in certain regions. If you can harvest these materials and run the right chemical reactions, you can produce methane and liquid oxygen, exactly the propellant SpaceX's Starship engines are designed to burn. The mission brings the equipment. Mars provides the raw ingredients. The factory runs on the surface for months before the crew ever arrives, filling propellant tanks slowly, steadily, until there is enough to launch a rocket back to orbit. The chemistry itself is not in dispute. The Sabatier reaction has been understood for over a century. You combine carbon dioxide and hydrogen under heat and pressure, and you get methane and water. The water gets electrolyzed, split by electricity into hydrogen and oxygen. The hydrogen feeds back into the Sabatier reaction. The methane and oxygen accumulate as propellant. It is an elegant closed loop, at least on paper, and it works reliably in industrial settings on Earth. But here is what most people don't realize. No one has ever run this process on another planet, not at any scale, not even close. In 2021, NASA's Perseverance rover carried a small experiment called MOXIE, the Mars Oxygen In Situ Resource Utilization Experiment. MOXIE was about the size of a car battery. It converted carbon dioxide from the Martian atmosphere into oxygen. It worked. The oxygen it produced was real. But MOXIE generated a few grams of oxygen per hour under carefully controlled conditions. It was a proof of concept. It demonstrated the chemistry was possible in the Martian environment. It was not a factory. It was a single instrument running in controlled test sessions, producing amounts of oxygen that would be essentially invisible against the backdrop of what a return mission needs. Scaling from MOXIE to a functional Mars propellant plant is not an engineering refinement. It is an entirely different category of problem. The ISRU system required for a human return mission would need to process vast quantities of Martian atmosphere and water, run continuously for months without human intervention, survive temperature swings that drop to -70 degrees Celsius at night, endure dust storms that can reduce solar power for weeks, and do all of this without a critical failure. Not one failure, not a small failure that engineers can patch. Any failure that stops the propellant production process for long enough puts the return timeline in jeopardy, and the system has to be pre-positioned. The crew cannot wait on Mars for the propellant tanks to fill after they arrive. The ISRU equipment would land on Mars years before the astronauts, running autonomously in a remote environment with no one there to fix it when something breaks. Mission planners would monitor it from Earth 18 minutes away by radio signal. If a component fails, by the time Earth knows about it, the crew may already be in transit. The engineering requirements compound quickly. The ISRU equipment needs power, enormous amounts of it sustained over months. Solar panels degrade in the Martian dust. Nuclear reactors could provide more reliable power but add mass and complexity. The water source that the Sabatier reaction depends on has to be close enough to the landing site to be practical. The production timeline has to align with the crew's arrival and the launch window. Every one of those dependencies has to hold simultaneously. None of this makes ISRU impossible. The chemistry is real. The concept is sound. Several serious engineering teams are working on it, but there is a significant distance between a sound concept and a functioning industrial system on another planet. and that distance has not yet been crossed. The entire return mission depends on a chemical manufacturing process that has never been demonstrated on another planet at anything close to the scale required. The Sabatier reaction that would produce the methane propellant for the return journey requires water. Not a small amount of water. Not a few liters collected from morning frost. The return mission needs more than 1,000 metric tons of Martian water to produce enough propellant and sustain life support across the full mission duration. That number has to come from somewhere on the surface of Mars. And here is where the problem gets genuinely serious. Mars has water. That part is true. But where that water actually is and whether it can be reached, processed, and used in time is a different question entirely. The most abundant water ice on Mars sits at the poles. The northern and southern polar caps contain enormous reserves of frozen water mixed with dry ice. From an engineering standpoint, the resource is real. But the polar regions are not where you want to land a crewed mission. Temperatures there drop far below what any human surface operation could reasonably sustain. The terrain is hostile. The lighting conditions are poor for solar power generation. The latitude creates additional challenges for communication and orbital mechanics. Early human missions are almost certainly going to target the equatorial regions, where conditions are more forgiving and landing approaches are more practical. The poles are where the water is confirmed to be. The equatorial regions are where the crews need to be. Those two facts are in direct tension with each other, so the question becomes whether accessible water ice exists anywhere in the equatorial or mid-latitude regions at depths that could actually be reached and harvested. The answer, as of right now, is that we don't know for certain. There is evidence suggesting subsurface ice may exist at various depths across a broader range of latitudes than just the poles. Orbital radar instruments have detected what appear to be ice-rich deposits beneath the surface in some mid-latitude areas. That's encouraging, but detecting something from orbit and confirming it's accessible at a depth a mission could actually reach are entirely different things. A reading from orbit doesn't tell you whether the ice is 1 meter down or 50 meters down. It doesn't tell you its purity. It doesn't tell you whether the extraction and processing equipment that lands nearby can actually get to it. Here's what makes this particularly difficult. The mission can't just land anywhere and hope for the best. The landing site has to be selected years in advance. The ISRU equipment has to be sent ahead of the crew, touchdown at that specific site, and begin producing propellant before humans ever leave Earth. That means the water source has to be confirmed, or at least assessed with high confidence, before the crew is committed to the journey. If the crew arrives and the water isn't accessible at the depth expected, or if the deposits turn out to be smaller than the remote sensing suggested, the propellant production falls short, and at that point, there is no backup plan. Robotic prospecting missions could help narrow this down. Send a lander to a candidate site years ahead of the crewed mission, drill down, test the ice, assess the extraction rate. That's a reasonable approach, but it carries its own uncertainties. A single prospecting lander samples one location. The subsurface ice distribution may vary across the landing zone. The ISRU equipment may land a few kilometers from where the prospector drilled. Whether the results from one robotic mission translate into reliable predictions for another site, even a nearby one, is not guaranteed. Think about what that means in practice. You are designing a mission architecture around a resource whose accessibility won't be confirmed until the equipment is already on the ground, in some cases after the crew has already departed Earth. The launch window doesn't wait. Once the crew is in transit, they're committed. They will arrive at that site regardless of what the ISRU system reports. If the equipment has been running for months and the propellant tanks are at a fraction of what's needed, the crew still lands. There is no abort option that gets them back to Earth from halfway through a 9-month transit. The research on this point is direct. Finding and validating a water source at an acceptable latitude and elevation is genuinely challenging, and it cannot be guaranteed in advance. That language from people who design Mars missions for a living is worth sitting with. They are not saying it's impossible. They are saying the uncertainty is real and the consequences of being wrong are severe. Every other part of the return architecture, the Sabatier reactors, the electrolysis systems, the propellant storage, all of it is downstream of this one fundamental question. If the water isn't accessible at the landing site or isn't there at all, the mission doesn't come home. Even if the ISRU equipment performs perfectly and produces every kilogram of propellant required, the crew still needs a rocket to leave Mars. That rocket has a name. Engineers call it the Mars Ascent Vehicle, and the fact that it has a name is nearly the most developed thing about it. No Mars Ascent Vehicle has ever been designed in full. None has been built. None has been tested. None has been approved for development by any space agency. It exists right now as a concept, a category of spacecraft that humanity has never actually made, representing one of the most critical single components in the entire mission architecture. If the propellant problem is hard, the Mars Ascent Vehicle problem is harder, because propellant is chemistry. The MAV is everything else. Here is what the mission requires. Before the crew ever leaves Earth, the ascent vehicle has to be sent to Mars first. It lands on the surface months before the astronauts arrive, possibly years before. It sits there. The Martian surface temperature swings from around 70 degrees Fahrenheit during the day down to negative 70 degrees Celsius at night. Dust storms can run for weeks. Fine abrasive particles get into every exposed surface. The vehicle has no crew to monitor it, no technician to service it, no engineer to notice a warning light and fix it before it becomes a failure. It waits, and then the crew arrives. They land. They spend months on the surface. At some point, they walk to the ascent vehicle, climb in, and fire the engines. That is the plan. That is the moment the entire mission has been building toward. Everything that came before, the 9-month transit, the landing, the ISRU operation, the surface work, all of it leads to that ignition sequence. It has to work. Not probably work. Not work with acceptable risk margins. It has to work, because there is no version of this where it almost works and the crew survives. If the engines don't ignite, the crew is on Mars. If a seal has failed during the months of sitting in the cold, the crew is on Mars. If the propellant has been contaminated or stored incorrectly, or the transfer lines have been compromised by thermal cycling, the crew is on Mars. There is no alternate vehicle. There is no backup sitting nearby. The closest rescue mission is on Earth, and the earliest it could possibly reach Mars is 2 years away. Think about what 2 years means in that context. A crew stranded on the Martian surface with a failed ascent vehicle would need to survive on the life support and supplies they brought without the ability to return, while a rescue mission is designed, funded, approved, built, launched, and flown. That is not a realistic scenario. That is not a plan. That is people dying slowly on another planet while Earth watches. What makes the Mars Ascent Vehicle different from other hard problems in this mission is the total absence of any experience base. Every other rocket humanity has built was built on Earth. It was tested on Earth. Engines were test-fired on the ground dozens or hundreds of times before they were trusted to carry a crew. The launch environment on Earth is well understood. The MAV gets none of that. You cannot fire a Mars Ascent Vehicle on Earth and call it validated, because Earth and Mars have different gravity, different atmospheric density, different temperature cycling, different dust. The environment that will try to break this vehicle is the one environment you cannot replicate for testing. So engineers will build the best vehicle they can, test it as thoroughly as Earth allows, and then landed on Mars and hope the gap between their models and reality is small enough. The ascent itself is, in purely mechanical terms, more achievable than landing. Mars has lower gravity than Earth. Its atmosphere is thin. A single-stage ascent to Mars orbit requires far less energy than an Earth launch. That part of the physics is on your side. But physics being favorable and hardware being reliable are different things. An ascent vehicle that has spent 18 months on the Martian surface before its first use is not a vehicle with a track record. It is a vehicle with a warranty that expired before the mission started. There is something almost disorienting about where this sits in the overall mission sequence. By the time the crew boards the Mars Ascent Vehicle, they have already survived the most radiation-intense journey in human spaceflight history. They have already executed the most complex landing ever attempted. They have already lived on another planet. And then, at the moment they are finally trying to come home, everything depends on a piece of hardware that has been sitting in Martian dust since before they left Earth, waiting for one chance to work. Not one chance to prove itself. One chance to work. A machine that has never been built, sitting on another planet for months before it ever fires its engines, and it has to work the first time. If you decided to abandon the ISRU approach entirely and simply bring all the return propellant from Earth, the numbers become almost incomprehensible. Here is what that actually looks like. To deliver roughly 35 metric tons of propellant to the Martian surface from Earth, you need to launch approximately 400 metric tons of propellant just to cover the losses of the journey. The fuel burns getting out of Earth's gravity well, it burns again for the transit. It burns for Mars orbital insertion. By the time anything reaches the surface, the vast majority of what you launched is already gone. You launched 400 metric tons. You got 35. That is the brutal math of deep space logistics, and it applies to every kilogram of every supply sent from Earth to Mars. But here is what makes those numbers collapse entirely. 35 metric tons is not even close to enough. The estimated propellant requirement for a crewed Mars ascent and return is around 1,200 metric tons. Not 35, not 100. 1,200. So if you scale that 400 to 35 ratio upward to cover the actual requirement, you are talking about launching roughly 14,000 metric tons of propellant from Earth. That is not a mission architecture. That is a fantasy. No launch system conceived or under development could support that supply chain in any practical time frame or at any conceivable cost. This is why ISRU is not a nice addition to the mission plan. It is the only reason a return mission is mathematically possible at all. The moment you take it off the table, the numbers don't just get worse. They stop being numbers you can work with. Now look at what this means for total mission cost. Estimates for a crewed Mars mission with a return component range from $100 billion on the optimistic end to more than $1 trillion depending on the architecture, the timeline, and what assumptions you make about reusability and commercial access to space. That is an extraordinary range, and the uncertainty itself tells you something important. Nobody agrees on what this actually costs because nobody has ever done anything remotely like it. The variables are too many and too large. To put the lower end of that range in perspective, the Apollo program cost approximately $280 billion in today's dollars. That was the most expensive peacetime government project the United States has ever undertaken. It required a workforce of 400,000 people at its peak. It consumed somewhere between 2% and 4% of the entire federal budget for nearly a decade, and it sent humans to the moon and back. The moon is roughly 240,000 miles from Earth. Mars, at its closest, is about 140 million miles away. That is nearly 600 times farther. The life support requirements alone scale with mission duration. Apollo missions lasted about 8 days. A Mars mission would last around 34 months. The $280 billion Apollo comparison is not meant to suggest that Mars costs exactly that multiple times more. Costs don't scale linearly with distance, but it frames what we are dealing with. Apollo was the ceiling of what a wealthy superpower could sustain under the extraordinary political pressure of a Cold War space race. A crewed Mars return mission would need to exceed that effort significantly, and it would need to do so without a Cold War, without a single clear national adversary driving urgency, and without the kind of bipartisan consensus that existed in the 1960s. The return component specifically drives a disproportionate share of that total cost. Think about what return actually requires. It requires the ISRU system. It requires the Mars Ascent Vehicle. It requires a return transit vehicle waiting in Mars orbit. It requires the propellant to fuel all of those systems. It requires the mass budget for life support across the return journey. It requires Earth re-entry capability at the end. Remove the return requirement and you eliminate most of that mass, most of that infrastructure, most of that complexity, and a substantial fraction of the total cost. This is exactly why one-way mission proposals keep surfacing among serious engineers and mission architects. It is not that those people don't care whether astronauts come home. It is that the return requirement is responsible for a majority of why the mission costs what it costs, and the economics become genuinely different without it. A one-way mission is not cheaper by a small margin. It is cheaper by an order of magnitude. That is a hard thing to sit with. It means the conversation about whether the first Mars astronauts come back is not purely a technical conversation. It is also a financial one. Every cost estimate that includes a return mission comes with a tail that extends toward $1 trillion. Every cost estimate that treats Mars as a one-way settlement looks dramatically different. The math does not lie, and the engineers reading these numbers are not ideologues. They are people staring at figures that don't work and asking what you remove to make them work. What you remove, more than anything else, is the return. The return journey, that single requirement, is responsible for a staggering share of why a Mars mission costs what it costs. The technical challenges are formidable enough on their own, but they are only part of the problem. Everything discussed so far, the propellant math, the ISRU systems. The Ascent Vehicle assumes that the mission is actually funded continuously for the entire duration it takes to pull it off. And that duration is not short. A human Mars mission requires more than a decade of sustained planning and execution before a single astronaut leaves the ground. That means budget requests. That means congressional approval. That means the same program surviving multiple presidential administrations with entirely different priorities, different advisors, different visions of what the country's space program should be doing. Here's what most people don't realize. The history of American spaceflight is not primarily a history of engineering failures. It is largely a history of programs that worked, technically, until they didn't get funded anymore. Constellation is the clearest example. NASA spent years and billions of dollars developing the Ares rockets and the Orion capsule under Constellation, a program explicitly designed to return humans to the Moon and eventually reach Mars. Engineers were making real progress. Hardware existed. Then a new administration reviewed the program and canceled it. Not because the engineering failed, because priorities shifted, the money stopped, and years of work were effectively abandoned. That happened with the Moon. Mars is an order of magnitude more complex. The political commitment required to see a human Mars mission through from initial funding to a successful landing and return is unlike anything American democracy has historically been able to sustain. Every 2 years, Congress changes. Every 4 or 8 years, the White House changes. Each new president arrives with their own vision of what NASA should be doing, what the country should be spending money on, what legacy their administration should be pursuing. There is a powerful temptation, almost irresistible, for each new administration to put their own stamp on the space program, to rename it, to redirect it, to build something that looks like theirs. Think about that for a moment. The first crewed Mars mission, under even the most optimistic projections, is still likely in the early to mid-2030s at the absolute earliest. A mission preparing now would need consistent political support through at least 3 or 4 presidential terms. The politicians voting to fund it today may be entirely out of office by the time the mission actually launches. The politicians in office when it launches may have had nothing to do with building it, and the voters who elected those politicians will have waited so long for results that the original logic of the investment is barely visible anymore. And unlike a highway or a hospital or a military base, a Mars mission does not deliver short-term benefits to any congressional district. No constituents are employed in large numbers in any single state because of Mars. No communities see their property values rise because NASA is developing a Mars Ascent Vehicle. The political economy of a Mars mission is almost entirely deferred. The payoff, whatever it is, scientific knowledge, national prestige, the establishment of a multi-planetary human presence, comes decades later. Politicians who operate on 2-year and 4-year cycles are being asked to fund something whose rewards land entirely outside their term in office. That is a genuinely difficult structural problem, and it exists completely independently of whether the rockets work. NASA's own internal projections have reflected this reality. An independent review board found that even a Mars sample return mission, no humans, just a robotic mission bringing back Martian rocks, could slip into the 2040s without significantly increased and sustained funding. That is not a human mission. That is a relatively small robotic program. And even that was struggling to survive the budget environment it was operating in. Scale that up to a crewed mission requiring hundreds of billions of dollars over 20 years. The political arithmetic becomes genuinely daunting. Some people point to the Apollo program as proof that sustained political commitment is possible. But Apollo had something a Mars mission doesn't have. It had the Cold War. It had the Soviet Union. It had a geopolitical rivalry so intense that Congress would fund almost anything NASA asked for because the alternative was falling behind. The space race was a proxy for something larger, something immediate, something that voters understood. A human Mars mission today does not have that driving urgency. It does not have a clear adversary breathing down its neck. The political will has to come from somewhere else, from a belief in scientific progress, from long-term national vision, from something harder to sustain than fear. The astronauts who will land on Mars will be trusting their lives to funding decisions made by politicians who may not yet be in office when those decisions are needed. For several years, one organization seemed to be moving faster toward Mars than anyone else in human history. That organization was SpaceX. And for a while, the pace of what they were building made the rest of the aerospace world look like it was standing still. Starship, the enormous, fully reusable rocket system SpaceX has been developing, was designed from the start with Mars in mind. Not the Moon, not low Earth orbit. Mars. Elon Musk said so repeatedly, and the engineering reflected it. The vehicle was built to carry large payloads across interplanetary distances and land them on surfaces with no launch infrastructure waiting on the other end. That goal was always Mars. In 2025, Musk stated publicly that SpaceX was targeting the 2026 and 2027 Mars launch window for the first uncrewed Starship flights to the planet. He gave it roughly 50% odds of hitting that window. The plan called for 5 uncrewed Starships to attempt Mars landings during that opportunity. If those missions succeeded, crewed flights would follow in subsequent launch windows. Think about what that timeline meant. It would have put humans on Mars sometime around 2029 or 2031. That was not a distant dream being gestured at on a slide deck. That was a stated operational target from the most capable private rocket company on Earth, backed by a vehicle that was actually being built and tested. Then, in February 2026, SpaceX announced it was delaying its Mars missions by roughly 5 to 7 years. The focus would shift to lunar missions instead. That announcement was quiet. It did not generate the same headlines that the original Mars ambitions had, but what it meant was enormous. The first uncrewed Starship Mars flights were now pushed into the early to mid-2030s at the earliest. Crewed missions even further. The most aggressive Mars timeline that existed anywhere in the world had just slipped by nearly a decade. Here's what that delay actually revealed. Starship is a genuinely remarkable vehicle. The scale of it, the reusability, the cargo capacity, nothing else in the history of spaceflight compares to what SpaceX has built. But building a rocket that can reach Mars and building a complete mission architecture that can land humans there and bring them home are two entirely different problems. The rocket is one piece. It is not the hardest piece. The specific capabilities a crewed Mars mission requires go far beyond propulsion. Propellant production on the Martian surface, precision landing of massive payloads in an atmosphere that is almost useless for braking, reliable ascent systems that have to work perfectly after sitting on Mars for months. None of these capabilities exist in a demonstrated, validated form. Starship can launch, it can be refueled in orbit. Those are real achievements. But the chain of technology between Starship launching from Earth and a crew safely lifting off from Mars is long, and most of its links are unproven. The orbital refueling problem alone is worth pausing on. Each Starship heading to Mars requires roughly 12 tanker flights just to fill its tanks before departure. 12 separate launches, 12 separate rendezvous operations, 12 cryogenic propellant transfers in orbit, all in a compressed window before the launch opportunity closes. That sequence has never been demonstrated at anywhere near this scale. The tanker architecture that makes it theoretically possible is still being developed. Getting that right is a precondition for everything else, and that is just the departure from Earth. What the delay signals is not failure. SpaceX has not given up on Mars. The company's entire identity is built around the idea that humans will become a multi-planetary species, and Starship is the vehicle designed to make that happen. But the decision to pivot toward lunar missions for 5 to 7 years is an implicit acknowledgement that the Mars-specific capabilities are not ready. The Moon is closer. The communication delays are manageable. The missions are shorter. Landing on the Moon allows SpaceX and NASA to test and validate the kinds of systems, landing at scale, surface operations, resource utilization, that Mars will eventually require. The Moon is a rehearsal. Mars is the performance. But rehearsals take time, and the performance keeps moving further out. A few years ago, serious people were drawing timelines that put boots on Mars before 2030. Now those timelines are gone. The early to mid-2030s is the new optimistic floor, and every major program in spaceflight history has demonstrated that optimistic floors tend to drop. The people making these decisions are not pessimists. They are engineers who looked carefully at what the mission actually requires and concluded that what currently exists is not sufficient. That is a meaningful conclusion from the most capable and motivated Mars-focused organization in human history. Even the most aggressive commercial space effort ever attempted looked at the full scope of the Mars return problem and decided it needed more time. More time to develop the landing systems, more time to demonstrate propellant production, more time to build and test a Mars Ascent Vehicle that does not yet exist. The ambition was never the issue. The gap between the ambition and the technology was. The delay didn't mean Mars was off the table. but it revealed that the gap between ambition and readiness was considerably wider than the most optimistic timelines suggested. Some serious people, engineers, mission architects, space policy researchers, have reached a conclusion that the rest of the space community tends to find uncomfortable. If returning from Mars is the hardest part of the mission, the most expensive part, the part that depends on unproven technology operating perfectly in sequence on an alien world, then there is a question worth asking directly. What if the first mission simply doesn't try to return? That question has been on the table longer than most people realize. In 1998, a space activist named Bruce Mackenzie stood up at the International Space Development Conference and made the case formally. His argument was straightforward. A one-way settlement mission would be simpler, it would be cheaper, and the scientific and exploratory value would actually be greater. This was because a crew that stays permanently can do far more than a crew that spends most of its time preparing to leave. The proposal didn't generate mainstream headlines at the time, but it planted a seed that serious engineers and mission architects have been quietly returning to ever since. Here's what the math looks like when you remove the return requirement. The Mars Ascent Vehicle disappears entirely. You don't need it. The ISRU equipment that would have to produce 1,200 metric tons of propellant is no longer mission critical in the same way. The 9-month return transit doesn't need to be supported. The rendezvous in Mars orbit doesn't need to happen. Each of those elements represented not just hardware, but years of development, testing, and funding. Remove them, and the mission that remains is dramatically smaller, dramatically cheaper, and dramatically more achievable with technology that either exists or is close to existing. The mass savings alone are staggering. The return journey is responsible for an enormous fraction of total mission mass. Every kilogram of propellant you need to produce or carry for the return trip requires more hardware, more infrastructure, more complexity. Strip all of that away, and the mission profile compresses into something that begins to look, at least on paper, like something humanity could actually attempt in the near term. But the engineering argument is only part of it. The harder question is the human one. Who would volunteer for a mission with no return? The answer, based on every public survey and every serious recruitment effort that has touched on the subject, is that the volunteers would not be hard to find. There is something in human nature that responds to the idea of being first, of being permanent, of planting something that doesn't come back. The question is not whether people would go. The question is what kind of people we would be asking them to be, what obligations we would carry toward them in return. Think about what the psychological experience of that mission would actually look like. The crew launches. They spend 9 months in transit. They land. And at some point, the reality settles into daily life, not as an abstraction, not as a decision made in a training room on Earth, but as the actual texture of existence. The sky above them is not Earth's sky. The horizon curves differently. Supply ships arrive on a schedule that depends on planetary orbits. Communication with everyone they have ever known runs on a 24-minute delay. This is permanent, not a deployment, not a tour of duty. Permanent. Some mission architects argue that framing matters enormously here. The early settlers of permanent colonies throughout human history often knew they weren't coming back. The Polynesian navigators who crossed the Pacific had no return route mapped out. The people who boarded ships for the Americas in the 16th and 17th centuries understood, many of them, that the life they were leaving behind was gone. What they were building was not a visit. It was a new life. The Mars version of that story would be the same structure, scaled to a distance so much greater that the word permanent takes on a weight it has never carried before in human exploration. The ethical questions are real, and they don't dissolve just because the historical analogy holds up. Those early colonial settlers were often desperate, coerced, or facing situations that left them few choices. We would be asking trained professionals in full knowledge of the terms to accept a one-way commitment. The ethical framework most mission thinkers apply is informed consent, the same framework that allows people to take extreme risks in other contexts. A mountaineer who accepts a dangerous summit, a test pilot who knows the odds. The argument is that adults with full information are capable of making that choice for themselves, that it is not our place to forbid them from making it. But informed consent only carries so much weight when the gap between what you consent to on Earth and what you actually experience years later on Mars may be wider than anyone can fully anticipate. You can consent to the idea of permanence. You cannot fully consent to the feeling of it. None of this has stopped serious people from making the case. The logic runs as follows. The return requirement is what makes human Mars missions borderline impossible under current technology and funding realities. Remove that requirement and the mission becomes achievable. The first humans to land on Mars as permanent settlers would contribute more to science, more to long-term colonization, more to the practical knowledge of what it takes to live there than any short-duration visit ever could. And they would do it at a fraction of the cost and complexity that a return mission demands. It is a logical argument that few people want to accept out loud, but the logic itself is genuinely hard to dismiss. The most famous attempt to actually build and execute a one-way Mars settlement mission ended not with the launch, but with a bankruptcy filing. Mars One was announced in 2012. A Dutch entrepreneur named Bas Lansdorp stood up and described a plan to send 4 human settlers to Mars in 2027 and to follow them with new crews every 2 years after that. No return journey, no Mars Ascent Vehicle, no propellant production system. The settlers would live out their lives on another planet, supplied periodically from Earth, and that was the point. The idea was not a stunt. Lansdorp presented it as a legitimate mission architecture, one that sidestepped the hardest problems by simply removing the requirement to come home. The public responded in a way that surprised almost everyone. More than 200,000 people submitted applications to be considered for the mission. 200,000. These were not all dreamers or people who didn't understand what they were signing up for. Many of them had thought carefully about it. Many understood that Mars was brutal and cold, and that the return trip was not part of the deal. They applied anyway. That number alone tells you something important about the human relationship with exploration. The problem has never been finding people willing to go. Media coverage was enormous. Mars One appeared in major newspapers and broadcast outlets around the world. It generated genuine excitement in the space community and far beyond it. For a few years, it felt like a serious contender. The timeline seemed aggressive, but not impossible. Lansdorp was articulate and committed. The mission concept was coherent on its surface. But when engineers looked at the actual plan, the gaps became clear very quickly. Mars One had no spacecraft in development. It had no rocket. It had no contracts with any launch provider. It had no credible path to the funding it would need. Estimates for a realistic one-way Mars mission still ran into the tens of billions of dollars, and Mars One had raised a small fraction of that. The organization was, in practical terms, a concept with a website and a selection process, but no hardware, no signed agreements, and no demonstrated ability to close the financial gap between what it had and what it needed. The organization declared bankruptcy in 2019. No rocket ever fired. No crew was ever selected in any final sense. The 2027 launch date passed into irrelevance years before 2027 ever arrived. It would be easy to dismiss Mars One as a failure of ambition, a cautionary tale about entrepreneurs who overestimate themselves. But that reading misses the more useful lesson. The concept itself was not fundamentally unsound. One-way missions genuinely do reduce the complexity and cost of Mars exploration in significant ways. Serious engineers at serious institutions have made that same argument in peer-reviewed settings. The problem was not the idea. The problem was everything required to execute it. Getting hardware from Earth to Mars requires rockets. Specific rockets. Specific rockets that have been designed, built, tested, certified, and contracted to a specific mission at a specific time. Mars 1 had none of that. Building a habitat that can keep 4 humans alive on the Martian surface for years requires life support systems that have been tested exhaustively. Mars 1 had none of that either. Selecting a crew, training them, designing their mission, building the tools they would need. All of it requires years of engineering work and billions of dollars before a single component leaves the ground. The gap between the concept and the hardware is not a small gap. It is an enormous one, and Mars 1 never closed it. What the Mars 1 story reveals most clearly is that one-way missions do not solve the hard problems. They solve some of them. They eliminate the return propellant requirement. They eliminate the Mars Ascent Vehicle. They reduce the mass budget significantly. But they do not eliminate the need for a reliable launch system, a functional habitat, a working life support system, food production, radiation protection, and a crew that can stay alive for years in one of the most hostile environments in the solar system. Those requirements exist whether the crew is coming home or not. They are just as technically demanding. They are just as expensive. Mars 1 behaved as though removing the return trip removed most of the difficulty. It doesn't. It removes one layer. The layers underneath it are still there. And yet, 200,000 people raised their hands. That is the detail that stays with you. Not the bankruptcy, not the missing hardware, not the failed fundraising, the hands. Somewhere out there, hundreds of thousands of people looked at a plan that explicitly offered no return trip, on a planet with no breathable air and no rescue service, and said yes. That is a real thing about human beings. The instinct to go, to be part of something that has never been done before, to put your name on a new world. That instinct is not rare. It is surprisingly common. The failure of Mars 1 doesn't mean one-way missions are impossible, only that the distance between a compelling idea and an actual functioning mission is nearly impossible to overstate. Walk through what the stranded scenario actually looks like in practical terms. 2 years before any crew departs Earth, the ISRU equipment lands on Mars. Robotic systems begin running. The Sabatier reactors start pulling carbon dioxide from the thin Martian atmosphere. Drills push into the surface, searching for water ice. The equipment begins producing methane and oxygen, kilogram by kilogram, slowly filling the propellant tanks that the Mars Ascent Vehicle will eventually need. For months, the numbers look reasonable. The mission planners on Earth watch the telemetry and cautiously update their projections. Then something goes wrong. It might be a dust storm. Mars gets them, regional storms that can last for weeks, sometimes longer, blanketing the surface in fine particles and cutting solar power to a fraction of nominal. The ISRU equipment runs on electricity. No power means no production. A 6-week storm at the wrong time doesn't just pause the propellant timeline, it erases months of work from the schedule. And the launch window for the crew does not move. The planets don't wait. Or maybe the water is the problem. The landing site was selected based on orbital radar data, suggesting accessible ice within a few meters of the surface. But when the drills go in, the ice is deeper than expected, or the concentration is lower, or the soil chemistry makes extraction far slower than the models predicted. The equipment works exactly as designed. The resource just isn't there the way anyone thought it was. The crew launches anyway, there is no other option. The conjunction window that allows a reasonable transit to Mars opens once every 26 months, and missing it doesn't mean waiting a few weeks. It means waiting 2 years. By the time the crew lands, the propellant tanks are at roughly 30% of what the return trajectory requires. Think about what that number means. 30%. The tanks aren't empty. The system didn't fail completely. It just didn't work well enough, and now 4 people are standing on the surface of Mars with a return vehicle that cannot lift them to orbit. Mission control is 18 light minutes away. When the crew reports the propellant shortfall, Houston won't hear it for 18 minutes. By the time any response arrives, 36 minutes have passed. There is no conversation. There is no Apollo 13. On Apollo 13, flight controllers and astronauts work through the night together, problem and response cycling back and forth in near real time, because the moon is only about 1.3 light seconds away. That kind of collaboration is physically impossible on Mars. Every exchange is a 36-minute loop at minimum. By the time a suggestion arrives from Earth, the crew has already tried 3 things on their own. The engineers on Earth are not useless. They run simulations. They model alternatives. They work every possible angle. But even the best solution takes time to transmit, and then more time to verify, and then more time for the crew to implement and report back. A troubleshooting conversation that would take 20 minutes on the ISS takes the better part of a day on Mars. A system that is actively degrading doesn't have that kind of time. Now add a second problem. The Mars Ascent Vehicle itself has been sitting on the surface for 2 years in conditions that would destroy most industrial equipment on Earth. Temperature swings to -70 degrees Celsius at night. Abrasive dust that works its way into seals and joints. Occasional storm-driven pressure changes. The vehicle was designed to survive all of this. But designed to survive and actually surviving without any degradation are different things. An ignition system component that was rated for 24 months of exposure is now in its 26th month. A seal that tested to specification in a vacuum chamber in California has been cycling through thermal extremes on an alien surface. If the ascent vehicle has a fault, there is no spare. There is no backup vehicle parked at a different landing site that a rescue crew could reach in an afternoon. The nearest help is Earth, and Earth is 140 million miles away. A rescue mission launched immediately would take 9 months to arrive, and it couldn't even launch immediately because the window might not be open. In the worst case, a rescue mission is 2 years away. The scenario doesn't collapse in a single dramatic moment. That's the part that's hardest to understand. The ISRU equipment doesn't explode. The ascent vehicle doesn't catch fire. The life support systems keep running. The crew is alive. They have food, water, oxygen. They have time, which is the cruelest part, because time with no path home is not a resource. It's a countdown. They run the numbers again. They look for alternatives. They try every configuration the mission planners prepared for. And slowly, the list of viable options gets shorter. One approach fails to close the delta V gap. Another requires components they don't have. Another depends on propellant they can't produce fast enough before the next return window closes. The situation deteriorates the way most catastrophic situations actually deteriorate. Not in a flash, but incrementally, each small setback narrowing the corridor of possibility until the corridor is gone. The first humans to die on Mars will not likely die in a single dramatic accident. They will simply run out of options, slowly, one by one. For the first humans to return from Mars, a specific sequence of events must unfold without a single critical failure anywhere in the chain. Start at the beginning. Years before any crew departs Earth, an ISRU plant lands on the Martian surface. It has to land cleanly. It has to survive the impact of arrival, the temperature swings, the dust. Then it has to power on. Then it has to work. Not eventually. Not after repairs. Immediately, because the clock is already running. The crew's departure window from Earth is fixed. The propellant tanks need to be full before those astronauts ever leave the ground. The ISRU system begins pulling carbon dioxide from the thin Martian atmosphere. It begins processing water ice drawn from beneath the surface. It runs the Sabatier reaction, converting those raw materials into methane. It runs electrolysis, splitting water into hydrogen and oxygen. Day after day, month after month, it builds toward a target of roughly 1,200 metric tons of propellant. That number, again, is not a typo. 1,200 metric tons. Produced by a machine that has never been tested at this scale, on a planet it is never operated on, without a technician nearby who can open a panel and fix what's broken. If the water ice is shallower than expected, the system falls short. If a dust storm runs for 6 weeks and starves the solar panels, production stops. If a single critical component seizes or corrodes, the whole process stalls. There is no warehouse nearby with spare parts. Assume the propellant production succeeds. The Mars Ascent Vehicle has also been sitting on the surface this entire time. Months, possibly longer. It has endured nights where the temperature drops to -70 degrees Celsius. It has been coated in fine Martian dust that works its way into every seal and joint. Its fuel lines have been filled with propellant produced by a system no one has certified for operational use. Now the crew arrives. They inspect the vehicle. They check the systems. And at the moment of departure, the engines have to ignite. Not probably ignite. Not ignite with a 90% success rate. They have to ignite. There is no second vehicle parked 2 kilometers away as a backup. There is no rescue mission that could reach the surface in under 2 years. The ascent vehicle fires its engines, the crew rises off the surface, and it has to reach Mars orbit. A single engine failure during ascent, a fuel line rupture, a guidance system fault. Any of these ends the mission permanently on the surface. Assume the ascent succeeds. The crew is now in Mars orbit. They have to find the return vehicle. They have to match velocities with it, dock with it, and transfer aboard. Orbital rendezvous is not simple. It has been done many times in Earth orbit. It has never been done in Mars orbit with a crew that has already been on the Martian surface after months of physical deconditioning, after a 9-month journey through deep space, after whatever failures and emergencies have already accumulated by this point in the mission. Miss the rendezvous, and the options narrow quickly. Assume the rendezvous succeeds. Now comes the return transit. 9 months. The return vehicle has to sustain life for 9 more months of deep space travel. Its life support systems have to function without failure. Its radiation shielding, inadequate as it is, has to hold together. The crew, already weakened, already carrying whatever radiation dose they accumulated on the way out and on the surface, has to endure another 9 months of galactic cosmic ray exposure. Their bones are thinner than when they left Earth. Their cardiovascular systems have adapted to reduced gravity. Their eyesight may have already been altered by intracranial pressure changes that set in months ago. Then Earth. Re-entry. The vehicle hits the atmosphere at interplanetary return velocities, faster than a spacecraft returning from low Earth orbit. The heat shield has to perform. The parachutes have to deploy. The landing systems have to function. After 34 months away, after everything the mission has put through these systems, the final 8 minutes above Earth have to go right. Here is what that sequence looks like written plainly. Pre-positioned ISRU equipment survives landing. ISRU finds accessible water and processes it successfully. ISRU produces 1,200 metric tons of propellant over many months without critical failure. The Mars Ascent Vehicle survives the same months on the surface without critical degradation. The ascent engines ignite and deliver the crew to orbit. The crew successfully rendezvous with the return vehicle. The return vehicle sustains life through 9 months of deep space transit. The crew survives re-entry and landing after 34 months of physical deterioration. That is the checklist. That is every major link in the chain. Each of those links depends on the ones before it. None of them have a track record. None of them have been rehearsed on Mars, because nothing has ever been rehearsed on Mars at this level. The entire sequence has to work as a system, not as the collection of individual technologies, and the margin for systemic failure across 34 months is essentially zero. Every one of those steps has to work in the right order on a planet where none of them have ever been attempted before. None of this means humans should not go to Mars. Everything we've covered, the radiation, the propellant math, the unproven technology, the years of isolation, none of it adds up to a reason not to go. It adds up to a reason to understand exactly what going means. And that is a different thing entirely. The history of exploration is not a history of certainty. It is a history of people who looked at terrible odds and went anyway. The Polynesian navigators who crossed the Pacific didn't have charts or satellites or any way to call for help. They had stars, wave patterns, the behavior of birds, the accumulated knowledge of people who had tried before them and sometimes hadn't come back. They crossed thousands of miles of open ocean in wooden boats. They found islands nobody else had found. They went because the next place was out there, and that was reason enough. The first Europeans to attempt Atlantic crossings knew that ships had disappeared on that route. They knew that the maps ended somewhere and that beyond those edges, there was no reliable information. Some of them didn't return. The ones who did changed what humanity thought was possible. That pattern has repeated itself across every age of exploration. Someone goes first. The odds are not good. They go anyway. The astronauts who will eventually stand on Martian soil will know more about the risks facing them than any explorer in human history. They won't be sailing into the unknown with incomplete maps. They'll have radiation exposure data, bone density projections, propellant production estimates with error bars, psychological profiles built from decades of analog research. They will know the numbers. They'll know what 0.66 sieverts means. They'll know what bone mineral density loss looks like after 9 months in deep space. They'll know, in precise technical language, exactly how many things have to go right for them to come home. And some of them will still raise their hand and say they want to go. That is not recklessness. That is something older than recklessness. There is something in the structure of human cognition that points outward toward the next ridge, the next coastline, the next question that doesn't have an answer yet. We are not particularly well suited to stopping at a boundary and deciding that the other side isn't worth the cost. Mars is simply the latest version of a problem our species has been solving, imperfectly and at great cost, for as long as we've been a species. Think about what the first humans to land on Mars will actually experience. They'll step out onto a surface that no human foot has ever touched. The sky above them will be a pale, dusty orange. The gravity will feel lighter than anything they've known on Earth. In every direction, they'll see a world that formed 4.5 billion years ago. A world that may have had liquid water on its surface. A world that might, in some crease of ancient rock, hold evidence that life existed somewhere other than Earth. They will be the first human beings in history to stand on another planet. Whatever else is true about that moment, it will be one of the most extraordinary things our species has ever done. The first Mars astronauts may have already accepted that they won't come back. Maybe the mission architecture requires it. Maybe circumstances make return impossible. Maybe they simply understood the odds clearly enough that they made their peace with the outcome before they ever left. They will still go. That choice, to go knowing you may not return, is not a new kind of human behavior. It is the oldest kind. Consider what these astronauts are made of. Every atom of carbon in their bodies was forged inside a star. The calcium in their bones, the iron in their blood. These elements were produced in stellar cores and scattered across space when those stars died. Billions of years before Earth existed. The same nuclear physics that drives fusion inside a red supergiant is what powers the sun that kept this planet warm, long enough for those atoms to eventually assemble themselves into something that could look up at the sky and wonder what was out there. We are not separate from the universe we're exploring. We are part of it. We are the universe looking at itself. The rocket engines that will carry humans away from Earth toward Mars run on chemistry that obeys the same physical laws that govern everything from the largest star ever measured to the smallest atom in a Martian dust particle. That continuity is not a poetic idea. It is a physical fact. And it suggests something about why we go, not because the math is comfortable or the return is guaranteed, but because the impulse to understand, to reach, to go further, is not separate from the nature of the universe. It may be one of the things the universe does, expressed through us. Mars will be the hardest thing our species has ever attempted. The people who go first will face risks that no engineering can fully eliminate. Some of them may not come home. Some of them may have understood that from the beginning and decided the destination was worth the cost of the journey. That calculus has never been easy and has never stopped anyone who was truly determined to go. The stars have always been a long way away, and getting home has never been guaranteed. But we have always gone anyway.